Hello, welcome to the probability class. Today we will discuss about random variables. It's a very important concept in probability theory, something like numbers in daily life. Let me bring out the PPT so that I can start discussing on that. Here it is. What's a random variable? It's a predefined way of getting a number out of a random experiment. Predefined way of getting a number. Here are some examples. Suppose I go to the bus stop and wait for a bus. So waiting time to get a bus, that's a random variable. Look at the term predefined. I have to know beforehand what I'm looking for. I may look for this, or even for the same thing, while waiting for the bus, I might actually wait for a bus with vacant seat. Then my random variable is something else. Or I might wait to get an AC bus. So it depends on what's the thing that I'm interested in. But whatever it is, I will have to define that thing before I perform the experiment. That's why predefined way of getting a number out of a random experiment. Some other similar examples, height of a randomly selected person. So here the experiment is, you randomly select a person and then the measurement you take is the height of the person. Similarly, weight of a randomly selected person, that's also a random variable. Number of heads out of 3 tosses of a coin. So you toss a coin 3 times, and after the experiment is performed, you count the total number of heads. That gives you a random variable. Another example here, throw a pair of dice and the outcomes that you get on these 2 dice, you add them up, sum of the 2 dice. So that's again a random variable whose outcome, whose value depends on the outcome of the random experiment. Range of possible values. Every random variable has a range of possible values. Say, for example, when we count the number of heads out of 3 tosses, what are the possible values for that? It may be 0 if the outcome is T, or it may be 3 if the outcome is head, or it may be 1, say for example, if it is HTT, and so on. That's why the set of possible values for this random variable is 0, 1, 2, and 3, this one. Similarly, when you take sum of 2 dice, the possible values of that random variable are 2, 3, 4, up to 12. Now, waiting time for a bus, you don't know exactly how long you are going to wait. Suppose you measure in seconds. Okay, maybe you are having a stopwatch and measuring it in time, in seconds, or in smaller units, say milliseconds or whatever. Then you know that you will have to wait some number of seconds, which is definitely more than 0. But exactly how long you will have to wait, you don't know. So to be on the safe side, you are including all the positive numbers. All the positive numbers. Although, say, you are sure that you cannot wait more than a day. Say a day has got how many seconds? 86,400, something like that. So it cannot be more than this thing practically. It cannot be more than, I guess that is correct. That is number of seconds in a day. So 60 into 60 into 24, whatever it is. So many seconds are there in a day, and practically nobody waits for a bus more than a day. So it's enough to consider up to this thing, but it doesn't hurt even if you consider all the positive numbers. That's why we have kept here 0 to infinity. Now, weight of a random person or randomly selected person in kilogram, maybe you keep all the numbers from 0.5 up to infinity. So what's the upper bound of weight of a person? If you don't know, you include all the numbers. If you are not sure that someone must be greater than half a kilo, then maybe you keep all the positive numbers. Here we are keeping 0.5 to infinity. We are keeping 0.5 to infinity, assuming that nobody will weigh less than half a kilogram. Now, temperature on a day on the planet Earth in Celsius maybe will be within this range. Wherever you go, whichever day you take the temperature, it goes from -70 to 65. Or if you want to be a little safer, maybe you want to keep -100 to 100. However, if you go to some other extraterrestrial planets, say for example, some say Venus or Saturn or Moon, this range might not be enough. Number of tosses to get a head. Look at this. Number of tosses to get a head. What's the experiment here? You keep on tossing the coin, and as soon as you get a head, you stop. So the outcome may be this or this or this and so on. Now, total number of tosses you are counting. So that is 1 here, here it is 2, here it is 4, and so on. That's why the possible values of the random variable are 1, 2, 3, etc. All the positive integers. Compare this thing with sample space. Sample space gives you set of all possible outcomes. That's very important. Here, we are considering the range of possible values for the random variable. It's nice to know what are the possible values for a random variable, although it's not always essential. Consider any random variable x. What's a random variable? We already know that thing. It's a predefined way of getting a number out of a random experiment. Now, you perform the experiment. Here is the experiment. Once you perform the experiment, you get an outcome. For one round of experiment, you get one outcome. And once you get the outcome, your value of the random variable x is known. Say, for example, when we roll 2 dice, our outcomes may be 1, 1 or 2, 1 or 5, 6, etc. Now, we are counting sum of the 2 dice. Now, if the outcome is 3, 5, then what is the value of x? It's 8. So let's come to this thing. We perform the random experiment, and once that is done, the outcome is known. And once the outcome is known, your random variable is known. There is no more uncertainty in that thing. So the value of the random variable is completely determined by the outcome of the random experiment. Typically, outcomes of the random experiment we denote by the symbol omega. You may use any other symbol as well. Now, the value x corresponding to the outcome omega is denoted by x omega. Let's take an example. This one. We are tossing a coin 3 times. So the possible outcomes are HHH, HHT up to TTT. Now, if the outcome is, and what are you doing? In this example, we are counting total number of heads out of the 3 tosses. So if this is the outcome, what's the value of x? Then x equal to 0. If this is the outcome, then what's the value of x? Value of x equal to 2. If HTH is the outcome, then what's the value of x? 2. And notice we are denoting that value by x within parenthesis, the outcome. So x within parenthesis HTH is equal to 2. And x in this case is the number of heads out of the 3 tosses. Similarly, this thing. Often, we need to consider events written in terms of random variables. An expression of random variable x, let me give some examples. Say x equal to 5 or x less than or equal to 5 or x greater than 5 or x square equal to 4. Look at these things. These are all expressions involving the random variable capital X, and the expressions are either equality or inequality. Expressions involving equality or inequality in terms of X. What's the meaning of these things? Here is the meaning. Such an expression denotes the event of all outcomes for which the corresponding values of x, remember, for every outcome there is a corresponding value of the random variable x. So we are considering the event of all outcomes whose corresponding x value satisfy the given condition. In other words, when we consider x equal to 5, this is actually an event, and it means all the outcomes whose corresponding x values are equal to 5. When we write this thing, x greater than 5, we mean the event of all outcomes for which the corresponding x values are greater than 5, and so on. Similarly, this one gives you the meaning of an event of all outcomes whose x value when squared gives us 4. So such an expression of inequality or equality actually denotes an event. Keep that thing in mind. Let's look into this example. X denotes the number of heads out of 3 tosses, and we are considering the event x less than or equal to 1.3. Now, which all outcomes satisfy that? HTT, this has exactly one head. So x value of HTT is equal to 1. That's why HTT belongs here. Similarly, THT also belongs here. TTH and TTT. What's x of TTT? That's equal to 0. So that also, this outcome TTT also satisfies this. Here, look at the event capital X less than or equal to 1.3. It means all the outcomes. Omega, remember, represents outcomes of the random experiment. All omegas for which the X values are less than or equal to 1.3. And we get these 4 outcomes. The other 4 outcomes don't satisfy the given condition. Say, for example, HHH, HHT, HTH, or THH, these 4 don't satisfy this thing, this condition. Why is it so? Here the X value is 3, here the X value is 2, so is this one, and here also X value equal to 2. So all these X values are in fact greater than 1.3. That's why these outcomes don't come here. How about this? Which all outcomes have corresponding X value equal to 1.3? None of them that we know. For this particular example, we know the possible values of X are 1, 0, 1, 2, and 3. That's why this is equal to the event of null set, as no outcome satisfies the condition. Now look at this event, capital X greater than -1. Clearly, all the outcomes satisfy that because all the X values are either greater than or equal to 0. So for each outcome, this condition holds good. That's why capital X greater than -1, this is whole of the sample space. Suppose X is a random variable in any experiment, not only when we are tossing a coin 3 times. Consider a general random variable capital X. Now let's consider these 3 events: X less than or equal to 1, X greater than or equal to 5, and X is between 2 and 3. Now we have the concept of mutually exclusive and exhaustive collection of events. I repeat, we know what we mean by mutually exclusive collection of events and exhaustive collection of events. Let's see if this collection of events, these 3 events, are mutually exclusive. Yes, they are, because none of these 2 events can happen simultaneously or can occur simultaneously. Say, for example, if you take this and this, the question is, can they happen or occur simultaneously? No, because if the X value corresponding to the outcome satisfies 2 less than or equal to X value less than or equal to 3, then at the same time, it's not possible to satisfy this thing. That's why this is disjoint from this event. Similarly, this is disjoint from this one, and so on. All 3 events mentioned here are mutually exclusive of each other. That's why this collection of events is mutually exclusive. The question is this collection also exhaustive? The answer is no, because here we are considering a general random variable. I have not told you which random variable we are considering, what is the corresponding experiment, and so on. So without knowing that, we don't know if capital X equal to 1.5 is a possible value, right? Given this information that whatever we are given here, we are not sure whether capital X equal to 1.5 is a possible value or not. So it may be a possible value, and when we are not given some information, we cannot assume the contrary. So we'll have to assume that it is also a possible value. Now, what happens if this value occurs? Let's see if that is covered in one of these three sets. None of the three events covers this case. Say, for example, capital X less than or equal to 1, definitely does not cover this. Capital X greater than or equal to 5, no. And so does this one. 2 less than or equal to X less than or equal to 3, this event also doesn't cover this particular outcome. So here is an outcome which is not covered by any of the three events. That's why this collection of three events is not exhaustive. So this collection of events mentioned here is mutually exclusive. This is correct, but this is not. Now, instead of this, if you consider this thing, X less than or equal to 1, X greater than or equal to 5, and 0 less than or equal to X less than or equal to 6. In that case, this collection becomes exhaustive, right? Because no matter which value of capital X you get, you are covered by at least one of these events. Please notice I am using the term at least one of them, maybe more than one event, but at least one of the events will cover that. Say, for example, if I take now X equal to 1.5, then what happens? X equal to 1.5 is covered by this, right? It's covered by this. What happens to, say, X equal to 0.7? What happens to this? That's covered by this one as well as this one. Let me mark those. This particular outcome, capital X equal to 0.5, satisfies this as well as this one. Similarly, if you take any other value of capital X, that will be covered by at least one of the three events. However, they are not mutually exclusive, because if you take capital X equal to 0.7, then that value is covered by both these events or satisfied by both these events. That means these two events, capital X less than or equal to 1 and capital X between 0 and 6, they are overlapping events. In other words, they are not mutually exclusive. That's why this collection is also not mutually exclusive. Look at this event, capital X square equal to 4. That means it's the event of all outcomes whose X values when squared gives you 4. When the X value square of the outcome becomes 4, then the corresponding X value must be equal to 2, or it must be equal to -2. There is no other possibility. Say we have got one outcome and the corresponding value is X value is this, and when you take square of this thing, you are getting 4. That's the meaning of this, right? Now, if that thing happens, then you can say that X value must be equal to 2 or -2. That's what we are writing here. That means X square equal to 4 implies either this or this. Either this thing happens or this thing happens. And conversely, if capital X value equal to 2, then this event occurs. and when capital X equal to -2, then also this event occurs. So that's why we can say that this event capital X square equal to 4 is union of these two events, X equal to 2 and X equal to -2. In fact, we can write it in set terminology as X square equal to 4. This event is same as X equal to 2 event and union of X equal to -2 event. Please note that these two events, X equal to 2 and X equal to -2, are mutually exclusive or disjoint. They are disjoint. Why is it so? Because when capital X equal to 2, at the same time, it cannot be equal to -2. That's why they are disjoint. So you are breaking it up into two mutually exclusive events. That's not important here. Just I wanted to make sure that you understand this event. What's the meaning of this event? And it actually breaks down into two sub-events. Now we come to two types of random variables. Those are discrete and continuous. What is a discrete random variable? One random variable whose range of values. What is the meaning of range of values of a random variable? That means possible values of the random variable, whose range of random variables doesn't contain any interval of real numbers. Here is the real number line, 0, 1, 2, -1, -2, etc. This is the set of real numbers. We typically use the letter R like this to denote the set of real numbers. So this one, the range of values of the random variable must not contain any interval like this. It must not contain, say, for example, 0 to 3 or -1 to say 2 or 5 to 5.001. It must not contain any interval. Then it will be called a discrete random variable. In other words, the values are discrete points on the real number line. The values, possible values of the random variable are like discrete numbers. It is not a whole continuous interval. That's why the term discrete. The other type of random variables is continuous. And the property of that thing is exactly the other type. Here, in case of discrete, it doesn't contain any interval. And in case of continuous, it contains some interval of real numbers. That is either, say, 0 to 5 or 0 to infinity or -1 to, say, 0.5. Some such interval must be part of the range of values of the random variable. In that case, you call it a continuous one. Let's look into examples of both the types. Suppose we toss thrice and count the number of heads. In that case, the possible values are 0, 1, 2, and 3. Clearly, it does not contain any interval of real numbers. So, this is discrete. Sum of two dice thrown together. What are the possible values there? 2, 3, 4, up to 12. Again, the range of possible values are just discrete numbers, some set of discrete numbers. That's why this is also an example of discrete random variable. Now this example, number of tosses required to get a head. What are the possible outcomes here? it may be head or maybe tail head or tail head. These are the possible outcomes. And what are the corresponding values of the random variable? Total number of tosses is here 1, 2, 3, 4, etc. So the range of possible values for the random variable are 1, 2, 3, 4, etc. See again, these are discrete points. When you draw these things, these numbers on the real number system, on the real number line, you get discrete points. But it does not cover any complete interval. That's the point. That's why this is also discrete. Now, what happens about the waiting time for a bus? The set of possible values here is 0 to infinity. So it contains an interval. That's why it is continuous. Similarly, weight of a random person or randomly selected person, that is also continuous. Temperature on a day, we had kept minus 70 to 65. This is also an interval. So all these examples are of type continuous. So hope you understood these two types clearly. One is discrete, where the possible values come as discrete points on the real number system. The other one is continuous, where the range of values covers some interval of the real number line. Here is a critical example. Read this, these points. Keep rolling a die until you get a 6. So possible outcomes can be 6. If the first throw of the die produces 6, you stop. Otherwise, it may be like this: 2, 3, 1, 2, 1, 5, 5. Then you get 6. So you had to roll the die, in this case, 1, 2, 3, 4, 8 times. You rolled 8 times. So number of rolls may be anything. You might have to roll even 100 times to get a 6, or maybe 1,000 times. Theoretically, it's possible. Right? So let's make the following observations. What we are trying to do, we are trying to understand this example to classify this thing into one of the two categories, whether it is discrete or continuous. Now, each of the rows must be at least 1. Look at this example, 2, 3, 1, 2, etc. Here, all the rows are greater than or equal to 1. Similarly, each row gives at most 6, because the numbers that will appear in any of the rows will be 1 to 6, an integer between 1 and 6. That's why these two conditions are satisfied. And how many possible outcomes are there? It's quite clear, written this way, that the set of possible outcomes is actually infinite. You might write any sequence of numbers from 1 to 5 of any length, and then add a 6 at the end, and you get a possible outcome. Right? And for each possible outcome, you get the average of that thing, which gives you a possible value. So possible values here are infinite, because corresponding to each of those infinitely many possible outcomes, you get one average. Some of those averages will be same for two outcomes, that's possible, but total number of possibilities of the averages still will be infinitely many. Convince yourself. Now the question is written this way. See that this is the real number system. Here is 0, here is 1, and so on. Now, written this way, this is also a possible outcome. 1, 1, 1, 1, maybe say 100 times followed by 6. This is also a possible outcome of the random experiment. And in this case, the average will be 1 plus 1 plus 1, 100 times. That is 100 plus 6. That's why 100, 100 ones followed by 6. So what's the average of that thing? 106 divided by 101. So this is a number very close to 1, come somewhere here. And this way, written this way, you can get arbitrarily close numbers to 1. You may get x values arbitrarily close to 1, very close to 1, as close to 1 as you wish. Something like those who know, say, calculus a little bit can appreciate this concept. You can get possible values of x as close to 1 as you wish by making appropriately suitable outcomes. And here we are just observing the set of possible values. Okay. Now, the question is, does it contain any interval of real numbers? That's the question. Does it contain any interval of real numbers? So, let me go to the next board so that I will get some more space there. There is a white space there. Yeah, here. The question is, does it contain any interval like this? Actually, it's not possible for this particular example. I'll tell you the reason. There is a property of real numbers which says that any interval like this, both rational and irrational, I'll read it out because my handwriting is extremely bad. Okay. This fact about real numbers tells you that any interval of real numbers, no matter how big or how small, always will contain both rational numbers as well as irrational numbers. What are rational numbers? The numbers which are of the form p by q, that is integer by integer. Like, say, for example, 2 by 5, 197 by 2000, all these are rational numbers. An integer divided by another integer. It may be positive or negative. Say, for example, this is also a rational number. And all the numbers which cannot be expressed in this way are irrational numbers. Some examples, √2, √3, minus of √2. These are all irrational numbers. Or say √3 by √2 or √3 by 5. These are all irrational numbers. So any interval contains both rational as well as irrational numbers. Now look at the way we are computing x. X equal to average of the throws, average of the rolls, right? So that means total of all the rolls, total divided by number of times we have rolled. And both of these things are integers, right? When you add all those things, all those rolls, you get an integer, and also total number of times, that's also an integer. So it's an integer divided by an integer. That's why x value in this example must be always a rational number. For this example, it's always a rational number. Now, look at this fact. Any interval must contain both rational and irrational. That's why the set of possible values of x must not contain any interval of real numbers. In other words, the range of values of x cannot contain any interval of real numbers. That's why this is an example of discrete random variable, although this random variable can take infinitely many possible values. Why this example is very critical? Because the way the values are taken, and we have seen that near 1, there are infinitely many values near 1, and the values may get as close to 1 as you wish. Still, the values, the random variable is still a discrete random variable. In other words, the values are still discrete numbers. Now let's talk about probability mass function. This is related to discrete random variable. And for the rest of the session, we'll be restricting ourselves to discrete random variable, and we will cover continuous random variable in the next session. Consider a discrete random variable capital X. Now, here, while talking about probability mass function, our capital X will denote a random variable and small x will denote a real number. So we are taking any discrete random variable capital X. Now fix any number x. X is a real number, I told you. So fix any value of x, say for example, x equal to 3. Then you consider the event capital X equal to small x. Say for example, if you have fixed x small x equal to 3, then you are considering x equal to 3. We have already seen that such an expression actually means an event, and as when we can talk about an event, we can also talk about its probability. So probability of that event capital X equal to small x, this is an event, and probability of that event is denoted by P of capital X equal to small x. So we come in step by step. We fix any value of real number, small x, then correspondingly we consider the event capital X equal to small x, and then we consider the probability of capital X equal to small x. Then we get a value. So starting from any number small x, we consider first the event capital X, start with any value small x, consider the event capital X equal to small x, then you consider the probability of that event capital X equal to small x, and that value gives you a number between 0 and 1. That number, we are considering a function small f, which is defined this way. Small f of x is same as probability of capital X equal to small x. Let me wipe out all these things. We are interested in probability mass function. What is probability mass function? Corresponding to the discrete random variable capital X, we are constructing a function. I repeat, we are constructing a function whose argument is a real number, and given an argument, it produces a real number. That's what is a function. It's given an argument and produces a value. Here the argument is also a real number, and what it produces is also a real number. Now, given the argument real number x, small x, it produces the number probability of the event capital X equal to small x. That's the way it is defined. So this is the definition of the probability mass function. In short, probability mass function is denoted by PMF. We in abbreviated form, we call it PMF. That is same as probability mass function. Let's take an example now. Okay, before example, Let me make sure this is the right screen. Yeah. Yes. Before considering an example, let us observe something. Suppose capital X is a discrete random variable, and suppose capital X takes values x1, x2, xn, etc. And if it takes only finitely many values, then it is of course x1 to xn, maybe x1, x2, x3, or x1, x2, x3 up to x5, and so on. So these are the possible values of the random variable. Now, if you take any other value, say a value x, which is not in this set x1 to x1, xn, etc., in that case, because that value is not possible, corresponding f value or f of small x will be equal to 0. Because what is f of x? That's nothing but probability of capital X equal to small x. And capital X equal to small x is impossible because small x is outside this set. So that's why capital X equal to small x will be the null set, and probability of null set is 0. That's why this thing happens. So we have understood this thing. Now, what about the possible values, or when the values are in the range of the random variable? Now, typically, if xi is a possible value, will be positive, typically. However, you remember that while discussing the possible values of a random variable, in many cases, we include some values which are actually redundant. But we just keep those things to make sure that it covers all the possible values. Say, for example, waiting time measured in seconds, it cannot be more than 86,400. Total number of seconds in a day. However, we keep all those numbers for theoretical possibilities. Say, if we are considering total number of days required to recover from malaria, say, we keep all the positive integers there. When we count the number of days, we keep all the positive integers, 1, 2, 3, etc. However, say, for example, 1 million, is it a possible value? Answer is no, because 1 million days, nobody will even survive. Forget about this thing, number of days required from malaria. No human being will survive, say, 1 million days. That's why there may be some redundant values in the set of possible values for which fxi is equal to 0. Otherwise, typically keep that thing in mind, f of xi will be greater than 0. And our target should be actually include only the things for which fxi is positive. Because otherwise, say, keeping redundant xi values actually doesn't help us. But sometimes we just don't want to waste time fine-tuning this set of possible values of the random variables and keep some redundant values. That's the only reason. So that's why I'm just additionally keeping this clause. Otherwise, it doesn't have much significance. Some example here. We roll a die and observe the outcome. This is happily a discrete random variable. 1, 2, 3 up to 6. These are the possible values. Now, what is the probability mass function of x? What is it? We need to determine the probability mass function. So we need to determine all the values for each of these 6 values. And anything other than that will be 0, that we have already seen, right? So it's enough to compute f1, f2 up to f6. How much is f1? f1 is equal to probability of the event capital X equal to 1. That means probability that the outcome is 1, and as each outcome of the each outcome of the die is equally likely, we get this probability equal to 1 by 6. Similarly, f2, f3, f4, f5, and f6, these are all equal to 1 by 6. And when we write them compactly in the form of a function, it looks like this thing. Fx equal to 1 upon 6 for the x values equal to 1, 2, 3, 4, 5, 6 and equal to 0 for any other value of x. What about this? Our pet example, tossing 3 times a fair coin, and x denotes the total number of heads. X can take values 0, 1, 2, 3, and it's enough to compute F0, F1, F2, and F3. And in order to do that, let's identify the events capital X equal to 0, 1, 2, and 3. What's the event capital X equal to 0? Which all outcomes satisfy that thing? Only the outcome triple T. Similarly, capital X equal to 1 is the event HTT, THT, and TTH, this one. Capital X equal to 2 is given by this event. The outcomes are HHT, HTH, and THH. All these 3 outcomes have the quality that the number of heads are 2. And similarly, capital X equal to 3 is the event, this thing. Now, the random experiment here is tossing thrice. And the set of possible outcomes, omega, is equal to HHH up to TTT. It has got how many elements? Size of omega is 8. And each of these 8 outcomes is equally likely. Remember that terminology that we used long time back while defining probabilities. Each of these 8 outcomes is equally likely. So what should be the probability of capital X equal to 0? That means probability of this event. Only one outcome is included here. That's why this is equal to 1 by 8. How about F1? F1 is what? Probability of this event. Capital X equal to 1. What is capital X equal to 1 event? That is the event, this one, which has got exactly 3 outcomes. That's why probability of that event must be equal to 3 by 8. Excuse me. Similarly, Similarly, F2 is equal to 3 by 8 and F3 equal to 1 by 8. So we have got all the values of importance. Next, we will write small f in nice function form. See this thing? We are writing all the calculations that we have done. We are capturing all these things compactly in the form of a function. And fx equal to 1 by 8 for x equal to 0. I'm just reading it out. For x equal to 1, it's 3 by 8. For x equal to 2, 3 by 8. For x equal to 3, 1 upon 8. And for any other value of x, it's 0. Consider another example. What is it? We have already seen this example. Keep on tossing a fair coin until a head occurs. We know already that this experiment has got infinitely many possible outcomes. Here we are counting the number of heads. That's denoted by capital X. And total number of heads in this random experiment can be 1, 2, 3, etc. because we are performing the experiment until a head turns up. So the possible values of X are 1, 2, 3, etc. So here we are trying to compute the PMF or probability mass function of the random variable capital X. In other words, we will be interested in computing small f of 1, small f of 2, small f of 3, etc. And once we can do that thing, we can write down the function f in a nice functional form. So read these things, and I'll go to the next page where I can get more space to write the things. So x can take values these things, right? And small f denotes the PMF of capital X. So small f of 1, that's what? Probability of x equal to 1. Which output corresponds to this? That means probability that the first toss is head. Then only capital X will be equal to 1. And what is the probability that the first toss is head? That's equal to half. Right? Now let's compute f of, say, 3. What is that? Probability of x equal to 3. That means probability of what? Probability that the first, second, and the third capital X equal to 3 happens if and only if these 3 things happens simultaneously. This one, this one, this one. So actually they are connected by and. So first toss is tail, and second toss is tail, and third toss is head. Now look at this. These are 3 events, right? Now these 3 events are talking about 3 different tosses. And the tosses are independent of each other. They don't influence each other, right? So because they don't influence each other, these 3 events must be independent of each other. So probability of these 3 events happening simultaneously, that is probability of the intersection of these 3 events must be equal to probability of the product of the probabilities. I repeat, probability of the intersection of these 3 events must be equal to product of the individual probabilities because they are independent. So it will be same as probability that first toss is tail multiplied by probability of second is tail multiplied by probability third is head. I didn't write these things in full, but you understand what I mean here. Now, what is the probability that the first toss is tail? It's a fair coin. So this is so this is half, and this is half, and this is half. So these 3 half multiplied together will produce 1/8. In other words, F3 equal to 1/8. That is same as 1/2 whole cube. Right? So writing similarly, now we can get, say, we can, once we understand this logic, we can write down Fn for any integer n. And that way we can write the formula of the PMF. The formula of the PMF is written here. See, for any possible value small x equal to 1, 2, 3, etc., f of x is given by the formula 1/2 to the power x, and it's 0 for any other value of x. So here is the final formula of the probability mass function for the random variable capital X. here are two properties of probability mass function. First, suppose capital X is a random variable, actually a discrete random variable. Capital X is a discrete random variable, and suppose x1, x2, xn, etc. are the possible values of the random variable. Again, if it takes only finitely many values, then it will stop at n, x1, x2 up to xn. Otherwise, it may go on up to infinity. Whichever be the case, these two conditions will hold good for any probability mass function. Property number one, fx value for any real number x will always be between 0 and 1. You remember similar property of probability? Probability of any event is always between 0 and 1. That's what is happening here. And the reason is also same. For any number small x, what is f of small x? That's nothing but probability of the event capital X equal to small x. And because it's a probability, it must be between 0 and 1. Right? That's why small fx is always between 0 and 1. Now, when we add up all the f values corresponding to the possible values of capital X, x1, x2, x3, etc. are all possible values of capital X. When we consider the corresponding f values or probability mass function values, we add them up, we must get 1. That's also an important property. I'll tell you why it happens. Say, when we take generally any collection of events, for a moment, let's step aside and consider any collection of events, say A1, A2, A3. Suppose they are mutually exclusive as well as exhaustive. So the diagram will look like this. Here is A1, here is A2, and here is A3. In that case, omega equal to A1 union A2 union A3, union A3. And when you take probabilities on both sides, we get probability of omega. Probability of omega is how much? That is equal to 1. And that is same as probability of this event, probability of A1 union A2 union A3. And remember, I told you that this is a collection of events which is both mutually exclusive. I don't remember exactly whether if I told you or not, but just assume that these three events, A1, A2, and A3, are mutually exclusive and exhaustive. Suppose we have got a collection of events A1, A2, A3, which are mutually exclusive as well as exhaustive. So this is the corresponding diagram, and omega becomes equal to A1 union A2 union A3 in that case. And then we can take probabilities on both sides. When you take probability of left-hand side, we get 1, because this is the whole sample space. And the right-hand side probability, because they are mutually exclusive, we'll break it down into 3 different probabilities, and we'll have to just add. So probability of A1 plus probability of A2. So this is a nice property of mutually exclusive and exhaustive collection of events. And that thing happens for any collection of mutually exclusive and exhaustive events. Maybe 3 or maybe 4 or maybe infinite collection of events. And that's what we will see here in an application. X1 to X1, X2, X3, etc. are the possible values. Now let's consider the events. These are all different events, and so on. Now each of these events is disjoint from other events. Say for example, capital X equal to X1 must be disjoint from capital X equal to X2, because at the same time, capital X value cannot be X1 as well as X2. It's not possible. That's why this is disjoint from this one. Similarly, any two of these events will be mutually exclusive. That's why this collection of events is a collection of mutually exclusive events. Are they exhaustive? The answer is yes, because no matter what's the x value, it must be one of these. So one of the events must be satisfied or must have occurred. That's why this collection of events is mutually exclusive as well as exhaustive. And what we discussed just now, in such a scenario, summation of their probabilities, x equal to x1 plus probability of x equal to x2, I'm just adding up all these probabilities, that must give me 1. And what are these things? Probability of capital X equal to x1, that is equal to f of x1, f of x2 plus f of x3, and so on, must be equal to 1. And that's precisely this property is. Summation of the f values of xi, f of xi, summation running over all the possible xi's gives us 1. Whenever a function satisfies these two properties, that's a possible candidate for probability mass function. Say, if somebody just gives us a function which satisfies these two properties, that there is these two properties along with a set of numbers x1, x2, xn. The properties are f values are between 0 and 1, and when you add up all the f values over those xi's, then you get 1. Suppose we are given a function, then that such a function is a possible candidate for probability mass function, right? Because although we don't know which is the random variable that corresponds to this probability mass function, but still it's a right candidate. So it's a right candidate for probability mass function in that case. Now let's identify among the following 4 functions which are right candidates for probability mass function. 1, fx equal to small x for all values of x. Is it a PMF? Is it a possible candidate for PMF? Answer is no, because f of 3 is equal to 3. That's greater than 1. It's not in the range 0 to 1. That's why this is not the right candidate. Let's look at this. Here we are given 3 values, x1 equal to -2, x2 equal to 5, and x3 equal to 7, right? What are the, for all other values, fx equal to 0, and for every value, the function when defined this way, please observe that for every value, fx is satisfying this. When x is one of these 3 values, then also when small x is one of these 3 values, -2, 5, or 7, then f values satisfies this thing. When it is not, when x is not one of these 3 values, then of course it is 0, then also it is satisfied. So no matter what is the value of x, this condition is satisfied. And what about this property? Let's check that thing. F of x1, that is equal to half. So this is equal to half, plus for the next value, it is 1/3, plus for the next value, it is 1/6, and that is equal to 1. 1/2 plus 1/3 is 5/6, plus 1/6 is 1. That's why property number 2 is also satisfied. That's why this is a right candidate for probability mass function, but this is not. How about this? Again, this is not, because here for some value, some x value, namely for small x equal to 3, f value is negative. F value can never be negative. It must be always 0 and 1. It must be always between 0 and 1. It cannot be negative. That's why this is also not a right candidate. How about this thing? We have, in fact, seen the random variable which produces this thing. I should say we have seen a random variable, because there might be some other random variables also which produce the same probability mass function. It's quite possible. However, we have seen an example which produces this probability mass function, and of course it should satisfy that thing, that property. But nevertheless, let's check again directly whether it satisfies both the criteria of probability mass function, property number 1 and 2. Property number 1 is obviously satisfied, because no matter whether x falls in this range 1, 2, 3 or not, fx is between 0 and 1. Now, what happens to the summation? We'll have to add up all these numbers. Now, this is a GP series. When there is a GP series like this, A is the first term and R is the common ratio. When mod R is less than 1, that is, R value is strictly between -1 and 1. In that case, this infinite series adds up to this number, A by 1 minus R. That we know. So this infinite geometric series will add up to, what's the first term here? First term is this one, 1 by 2. What's the common ratio? That's again half. So half by 1 minus half, and in the denominator is also half, so we get 1. That's why here also, when we add all the fxi values, we are actually getting 1. That's why this one satisfies both the conditions, and it's a right candidate for PMF. With this, we come to the end of this session. We discussed about general notion of random variables, then saw some examples, categorized random variables into 2 types, discrete and continuous. Continuous we'll cover in the next class. Today, we primarily discussed discrete random variables, the ones which don't contain any interval in the range of possible values. Then we talked about probability mass function, saw a few examples, and that's all about the session. Random variable, as I mentioned, is extremely important to deal with probability theory. So make sure that you understand these concepts very clearly. Those will be used left and right all through probability. Thank you for listening. See you in the next session.